In the context of astrophysics, the evolution and assembly of galaxies within the first billion years of the universe has garnered significant attention. High-redshift galaxies are expected to exhibit higher turbulence due to their smaller size, elevated star formation rates, and frequent mergers. Observations of galaxies at O-Z-4 support this scenario, showcasing increased velocity dispersion and decreased Vmax gas with redshift. The Atacama Large Millimeter, Submillimeter Array, ALMA, has enabled the study of gas kinematics in galaxies at Z greater than 4 through the observation of rest-frame farinfrared lines, such as C2 and O3, which serve as tracers of different interstellar medium (ISM) phases. Contrasting results have emerged from studies on gas kinematics in high-redshift galaxies, with some reporting velocity dispersions ranging from 20 km/s1 to 116 km/s1, while others found lower velocity dispersions and higher rotational velocities for massive starburst dusty galaxies. Cosmological simulations predict the existence of dynamically cold disks at Z greater than 6, with Vmax gas approximately equals 7. The observed evolution of gas kinematic properties can be explained by the increase in gas fraction with redshift, leading to a range of velocity dispersion in Vmax gas approximately equals 3.36. This study aims to understand the kinematic properties of high-redshift star-forming galaxies, focusing on their rotational velocity and velocity dispersion. A sample of 22 galaxies at Z greater than 4 was selected from the public ALMA data archive, with data calibrated using CASA and analyzed using moment maps and kinematic models. The researchers employed a rotational velocity model, VROT-R, accounting for disk and bulge components, and neglected dark matter contributions. The study also addressed the beam smearing effect, which can impact rotation velocity and velocity dispersion estimates. By comparing results with literature findings, the researchers assessed the dynamical state of early galaxies and discussed the evolution of velocity dispersion in Vmax gas as a function of redshift and physical galaxy parameters. The research paper presents a kinematic analysis of high-redshift galaxies using ALMA observations, focusing on the velocity dispersion and maximum rotational velocity of these galaxies. Two methods are employed for kinematic fitting. Method I, which uses a 2D kinematic fitting algorithm assuming a rotating exponential disk model, and Method 2, which applies a 1D kinematic fitting approach for galaxies without clear velocity gradients. Both methods derive kinematic properties by fitting C2 and O3 emission line observations. Method I yields velocity dispersion estimates ranging from 37 km/s1 to 132 km/s1. With a median value of 67 plus 1,513 km/s1, indicating turbulent but still rotationally supported disk galaxies. Method 2, after applying a correction factor of 1.6, yields velocity dispersion estimates between 37 km/s1 and 126 km/s1, with a median value of 60 plus 1,911 km/s1, suggesting slightly higher rotational support. The study finds that the velocity dispersion of C2 and O3 emission lines are similar, implying they trace different gas phases in the interstellar medium. However, the rotation to random motion ratios are lower on average compared to local galaxies and dusty massive galaxies at Z greater than 4. The authors also investigate the evolution of velocity dispersion in Vmax velocity dispersion ratio with redshift, comparing their results with previous studies and theoretical predictions. Figure 4 presents the evolution of gas velocity dispersion as a function of redshift from Z=0 to Z=8, consistent with the prediction by Wisniewski et al. 2015. The study's results suggest that high-redshift galaxies have higher velocity dispersions than previously thought, consistent with theoretical models, and provide new insights into the kinematics of high-redshift galaxies. Here is a combined summary of the 4 pages. The research paper investigates the kinematic properties of galaxies at redshifts greater than 4, focusing on velocity dispersion and the ratio of rotational velocity to gas velocity dispersion, Vmax equals gas. The analysis reveals that galaxies in the target sample and the alpine sample exhibit higher velocity dispersions and lower Vmax equals gas values compared to dusty star-forming galaxies, DSFGs. This discrepancy suggests that gas kinematic properties depend on both redshift and galaxy properties. In the SFR stellar mass diagram, the alpine sample and the target sample lie above the main sequence relation, indicating they are starbursts. DSFGs are more massive and consistent with high redshift starburst populations, but despite their high star formation activity, they seem to be less turbulent than High's main sequence galaxies. The paper explores the relationship between Vmax equals gas and galaxy properties such as stellar mass, dust mass, and gas fraction. Low-redshift studies have shown a dependence on Vmax equals gas and stellar mass, where more massive galaxies have higher Vmax equals gas values. The TNG50 and SARA simulations predict a similar or stronger dependence on stellar mass, respectively, with Vmax equals gas remaining almost constant for 6 less than Z less than 8. The study of gas velocity dispersion in high redshift galaxies reveals a median velocity dispersion of approximately 65 km s1, significantly higher than local galaxies and those at Z equals 12. The kinematic analysis using 2D and 3D fitting algorithms shows no significant bias in the recovery of velocity dispersion in Vmax equals gas due to beam smearing. The Vmax equals gas ratio as a function of redshift and stellar mass indicates that high redshift galaxies exhibit higher velocity dispersion than their low-redshift counterparts, regardless of their stellar mass. The gas velocity dispersion is also explored as a function of the SFR, suggesting that gravitational processes for galaxy-scaled turbulence driving are more likely responsible for the observed high-velocity dispersion, rather than feedback from star formation alone. The observed velocity dispersion agrees better with models that include both feedback and transport mechanisms, such as the Krumholz et al. 2018 model. The study examines the kinematical properties of high redshift galaxies, focusing on the relationship between velocity dispersion and star formation rates. Figure 10 illustrates the dependence of velocity dispersion on star formation rates and rotational velocity, considering 3 different models. The findings suggest that the high velocity dispersion of normal star-forming galaxies cannot be explained by star formation feedback alone and requires the contribution of gravitational instabilities. The analysis reveals that the ratio of rotational velocity to gas velocity dispersion, Vmax, sigma gas, does not show a clear dependence on gas fraction, but instead depends on stellar mass and dust mass. Galaxies with higher stellar mass tend to have more regularly rotating disks. The results contradict previous studies that found massive galaxies at similar redshifts to have low velocity dispersions and higher Vmax, sigma gas ratios comparable to local star-forming galaxies. The study uses a combination of observational data from ALMA and theoretical models to investigate the drivers of velocity dispersion, emphasizing the need for high-resolution observations and a higher signal-to-noise ratio to understand the evolution of velocity dispersion and rotational support of galaxies with redshift. The research paper also focuses on the analysis of galaxy kinematics using ALMA observations, examining the presence of turbulent disk galaxies at high redshifts. The authors employed 2 methods for kinematic analysis. Method I, which involves fitting the observed velocity field with a rotating disk model, and Method 2, which estimates the maximum rotation velocity from the width of the emission lines. To address beam smearing, the authors utilize a technique that uses only uncorrelated pixels in the likelihood estimation, providing more conservative and physical uncertainties on the free parameters. This method is tested and validated through simulations, reducing the error on the inclination parameter. The study highlights the importance of considering pixel correlation in kinematic analyses, especially when dealing with high redshift galaxies observed with ALMA. Here is a combined summary of the 4 pages. The paper presents an analysis of a sample of galaxies observed with the Atacama Large Millimeter, Sub-Millimeter Array, ALMA, focusing on the presence of turbulent disk galaxies at Z greater than 5. The authors provide a table detailing the properties of the analyzed sample, including stellar mass, star formation rate, and dust mass. They compared 2 different methods for kinematic analysis, Method I and Method 2, which involve fitting the data to a model of a rotating disk. The authors find that method 2 overestimates the velocity dispersion by a factor of 1.6 and apply a correction factor to correct this. The appendices provide additional details on the methods, including the reliability testing of method 2 by comparing its results with those from method I and discussing the limitations of the approach. The authors also present the results of 2D kinematic fitting, including moment maps derived from pixel-by-pixel Gaussian fitting, best models, and 1D distributions of free parameters. Similarly, they present the results of 1D kinematic fitting for galaxies with unresolved kinematics, recovering the radius and galaxy center by fitting the flux map for each target. The authors then present a comprehensive analysis of Mach data cubes to evaluate the performance of their method in recovering galaxy properties. They demonstrate that the method can accurately recover the galaxy properties, including scale radius, inclination, gas mass, and maximum velocity, even at lower signal-to-noise ratios and larger beam sizes. The results highlight the importance of considering the effects of beam size and signal-to-noise ratio on the recovered properties. Finally, the authors compare the velocity dispersion of the same galaxies obtained with two different methods, finding good agreement between the two methods. The corner plot distribution of the free parameters provides insight into the degeneracies between the parameters and the effects of the priors on the results. Overall, the analysis demonstrates the robustness of the method in recovering galaxy properties from Mach data cubes. The authors present kinematical fitting results for 6 high-redshift galaxies, utilizing the C2 and O3 emission lines to probe their internal dynamics. The fitting is performed using method I, involving Gaussian fitting to derive flux, velocity, and velocity dispersion maps. The results reveal complex velocity structures, indicating the presence of turbulent disk galaxies at z greater than 5, with high velocity dispersion values suggesting dynamically hot gas. Position velocity diagrams display signatures of rotating disks, with steeper gradients along the minor axis. The authors argue that the observed kinematical properties are consistent with turbulent disk galaxies in the early universe, but acknowledge uncertainties due to limited spatial resolution and signal-to-noise ratio. Future work aims to improve these aspects and extend the analysis to a larger sample of high-redshift galaxies. The authors also present C2 emission line observations for 7 high-redshift galaxies, showcasing their spatial distribution and diversity in emission line profiles. These observations, obtained with the ALMA telescope, provide valuable insights into the interstellar medium, turbulent gas motions, and starburst activity in these galaxies. The results suggest that turbulent disk galaxies may be more common at high redshift than previously thought, with implications for galaxy evolution and star formation in the early universe. The analysis of these observations highlights the importance of high spatial resolution and sensitivity in probing the internal dynamics of high redshift galaxies. The authors' findings shed light on the underlying physical processes that shape the evolution of these galaxies, emphasizing the need for further investigation to better constrain kinematical models and explore the drivers of observed turbulence. This study leverages Atacama Large Millimeter, Submillimeter Array (ALMA) observations to investigate the presence of turbulent disk galaxies at z greater than 5. The research focuses on the resolved C2 and O3 emission lines, which are crucial for understanding galaxy dynamics and star formation activity. The methodology employed in this study involves using ALMA observations to resolve the emission lines and estimate galaxy kinematics. A 3D fitting technique is applied to model the galaxy's velocity field, considering beam smearing and instrumental broadening effects. The velocity dispersion is calculated from the residuals of the 3D fitting, allowing for the estimation of the galaxy's turbulent motion. The results presented in figures F1 F.5 and F6 F.11 demonstrate that the observed galaxies exhibit high levels of turbulence, suggesting the presence of turbulent disk galaxies at high redshifts. This finding has significant implications for our understanding of galaxy evolution and the role of turbulence in shaping galaxy morphology. The fitting results for the 4 targets, VR7, CLM1, UVISTAZ004, UVISTAZ019, and Super 8, are consistent with the presence of turbulent disk galaxies at z greater than 5, as hinted by the ALMA observations. The observed spectra can be well described by a single-component Gaussian function, indicating that the emission lines are narrow and unresolved. The full width at half maximum, FWHM, of the Gaussian function is a measure of the velocity dispersion of the gas, which is a key parameter in understanding the physical properties of the galaxies. The study's limitations include the small sample size and the need for further observations to confirm the results. Future work involves expanding the sample size and exploring the relationship between turbulence and galaxy evolution.